A homomorphism is a way to compare two groups for structural similarities. It is a function between two groups which preserves the group structure in each group. So, let us be more specific. Suppose we have two groups G and H. Remember, G and H are different groups, and they may have entirely different group operations. To help us keep G and H separate in our minds, let's use an asterisk for the group operation in G and a dot for the group operation in H. We'll still use the word times, but we'll write the correct symbol for the operation. Now pick any two elements x and y in G. Let's say that x times y is equal to z. Next, suppose we have a function f that maps G to H. The three elements x, y, and z are mapped to elements in H. X is mapped to f of x, y is mapped to f of y, and z is mapped to f of z. So the whole point of a homomorphism is to find a structural similarity between two groups. So if x times y equals z in G, then we'd like f of x times f of y to be equal to f of z in the group H. But z equals x times y. Substituting this gives us f of x times f of y is equal to f of x times y. So this is the definition of a homomorphism. It's a simple definition, but it captures a big idea, a way to compare two groups. Take a closer look at the word homomorphism. It's a combination of homo, which means same, and morph, which means shape. But don't be misled by this name. If two groups are homomorphic, it doesn't mean they're the same. It just means they're similar. And that is for the definition of homomorphism. For examples, let's have Miss Sheila May Estareja and Giselle Raman.
Good day, everyone. I am Shalami A. Estariha, and I will discuss the example of homomorphism. So, first example, let G be the group of real numbers under addition and an abelian group with identity element 0, and each be the positive real numbers under multiplication with an abelian group identity element 1. So here's the homomorphism. Define the function f that maps x to e to the x. So to make sure this is a homomorphism, we need to verify that f of x plus y equals f of x times f of y. So don't forget that the group operation for G is addition, while the group operation for H is multiplication. So by the definition of f, this says that a to the x plus y equals a to the x times a to the y. So this is true. This is one of the rules of exponents. So f is a homomorphism.
Here's another example of a homomorphism. G will be the real numbers under addition, and H will be the complex numbers with absolute value 1. These complex numbers form a group under multiplication, showing this is a good exercise. So why don't you pause the video and show that H is a group? Here's a hint. In every complex number with absolute value 1 can be written as e to the I theta for some angle theta. Define the function f as f of x is equals to e to the ix. For f to be a homomorphism, we must have f of x plus y is equals to f of x times f of y. This is true when only if e to the I times x plus y is equals to e to the I x times e to the I y. We can see this is true by expanding the left-hand side. Then using the rules of exponents, it's true. So f is a homomorphism. By the way, I'd like to point out that f of a 0 is equals to f of 2 pi. Both are equal to 1. In fact, f of any multiple of 2 pi is 1. So this is not a one-to-one function. Homomorphism do not have to be one-to-one.